In this video, we're going to look at a different way of measuring angles. We're well aware that in a circle there are 360 degrees all the way around. 360 degrees in a circle, 360 degrees all the way around. What we need is a new way of measuring angles. And this is needed because when we look at trig functions, particularly their differentiation, we will need a different measure of angle from degrees. So let's have a look at what that measure is. So we take a circle, radius r, and I want to mark off on the circumference a length that is actually equal to r. So that distance around the circumference is equal to r, the radius. Now we join up there. That's r, and this angle here, theta, we describe as being 1 radian. So theta equals 1 radian. And if we want a definition of that, then the definition is the angle of 1 radian is the angle subtended at the centre of the circle by an arc that is equal in length to the radius of the circle. So that gives us our definition of a radian. Let me just draw 3 circles. Let's put that definition into effect again, where we've got a distance equal to r, the radius of the circle around the circumference, and there's our theta equals 1 radian. Now let me go round the circumference a distance of 2r. There's the radius again. Let's take halfway round. There. So that this is theta in here is 1 radian, and theta in here is also 1 radian. So what we can see there is that this distance 2r is in fact 2 radians times by the radius. And so that gives us a general formula that if we have any angle theta subtended at the centre of the circle, then the arc length s around there is given by s equals r theta. And that's the arc length, and it's true if theta is in radians. So that gives us a very good way of calculating the arc length when we know the angle subtended at the centre and we know its value in radians. So, can we get an equivalence between our radian measure and our degrees? Well, let's have a look at a circle again. The circumference of this circle we know by the formula 2 pi r. Now, let's compare that with our formula arc length. Our formula for arc length we know is r theta. Well, here's r and here is r. And what that means is that for this circle, the distance all the way round is 2 pi r, and therefore the angle in radians all the way round is this number here, 2 pi. So what we've got is that 2 pi radians is exactly the same as 360 degrees. Now this equivalence enables us to write down a whole series of equalities between angles. So we've got 2 pi radians is the same as 360 degrees. So pi radians is the same as 180 degrees, just dividing both sides by 2. If we divide by 2 again, pi by 2 radians, notice the way I said that, pi by 2, not pi divided by 2, but pi by 2. It's a shorthand. So pi by 2 radians is 90 degrees, and that's an important one because that's a right angle. Pi by 4, dividing by 2 again, pi by 4 radians is 45 degrees. So these are the important angles, so to speak. Some other quite important angles in trigonometry are 60 degrees. Well, 60 degrees is a third of 180 degrees. So pi by 3 radians is the same as 60 degrees. Another angle that's important is the angle 30 degrees. And 30 degrees is 1/6 of 180 degrees. So pi by 6 radians is the same as 30 degrees. Okay, we've got all of these equivalences, but the one thing we haven't got is how big is a radian in terms of degrees. 1 radian equals how many degrees? Well, we'll start with this relationship here, that pi radians is 180 degrees. So, pi radians is 180 degrees. So 1 radian must be 180 degrees divided by pi. And if we use a calculator to do that, we find that the answer is 57.296 degrees to 3 decimal places. Now, it's actually rare that we need to do this particular calculation, but what it does do is it gives us some idea of exactly how big a radian is. Now, so far, I've written down the word radian in full, but I haven't written down the word degrees in full. I've used this symbol, this little 0 up here, to signify degrees. So what do we do about radians? How can we signify a radian? So if we write down 1.5 radians, how are we able to tell that this is radians? Well, one way is to put a little C up there at the top, usually in italic print, if it's published in a book. So 1.5 radians. Another way is to write 1.5 rads, where rads is obviously short for radians. What we've done does not affect trig ratios. So, for instance, the cosine of pi by 3 is exactly the same as the cosine of 60 degrees, because the two angles are the same. The tangent of pi by 4 is exactly the same as the tangent of 45 degrees. And the sine of 3 pi by 2 is exactly the same as the sine of 270 degrees. One thing to notice here is that because I've got pi's in, I haven't written down a symbol because when we've got a pi in the angle, it's taken as read that these are measured in radians. So, we've got our formula S equals r theta, where S is the arc length and theta is in radians. What's the formula for S if theta is in degrees? Let's just have a look at our circle. There. Radius r. Our arc length S is around the circle like so. Radius r. And this angle in here, let's mark it as being theta degrees. So, what's our formula? Well, S must be a certain proportion of the whole circumference. S over 2 pi r. And the angle theta will be exactly the same proportion of 360. And so we can calculate the arc length S as 2 pi r, that's multiplying both sides by 2 pi r, times theta over 360. So there we've got our arc length formula for theta in radians, and here's our arc length formula for theta in degrees. Notice how much simpler this one is. What about another formula? What about the area of this sector? Well, let's have a look at that. Here's our circle again. Radius r. An angle theta. Let's call the centre of the circle O, and let's label the 2 points A and B. What's the area of this sector of the circle, this slice of the pie, so to speak? What's its area? Well, the area of the sector as a proportion or a fraction of the area of the circle must be the same fraction, the same proportion as the angle is of 2 pi all the way round. So the area of the sector, considered as a fraction of the whole circle, must be in the same ratio as the angle, considered as a fraction of the whole angle all the way round in radians. Well, we can work this out. Area of the sector, and we have a formula for the area of the circle. We know that's pi r squared equals theta over 2 pi. And if we multiply up by this expression here, the pi r squared, the area of the circle, then we have the area of the sector is equal to pi r squared times theta over 2 pi. And the pi's cancel, and that leaves me with a half r squared theta. And so for theta in radians, this is our formula. The area of a sector is a half r squared theta. Okay, we've got some formulae here. We've got some relationships. Let's have a look at how we can use them to do some calculations. So, in our first example, let's take a circle of radius 10 units, and let's take an arc length of 25 units. Now, if I make this a little more representative, 25 is more likely to be around there, 10 and 10. And the question is, what's this angle here in terms of radians and also in terms of degrees. So, what's our formula for arc length? That's arc length equals r times by theta if theta is in radians. So, S we know to be 25, R we know to be 10 times by theta. And so theta is 25 over 10, which is 2.5. And I can put a little c up there to stand for radians, or I could write it as 2.5 rads. So that's our angle in terms of radians. What will our angle be in terms of degrees? Well, one way might be to convert this answer here, this 2.5 radians, into degrees. Now let's remember that we had pi radians was 180 degrees. So 1 radian was 180 divided by pi degrees. So 2.5 radians must be 180 over pi times by 2.5. And we can use a calculator to work this out, and the answer is 143.2 degrees. Now let's have a look at another example. Start from the same point, that is, we've got a circle. We've got circle of radius 10 centimetres, and this time let's say we're going to take an arc length of 15 centimetres. And the question is, what is the angle in radians here at the centre, but also what's the area of this sector OAB? So let's begin with our formula for arc length. S equals r theta. Our arc length is 15, our radius is 10, and the angle is theta. So we divide both sides by 10 to give us theta is 15 over 10, which is 1.5 radians. Now, area of the sector, we have a formula for that. Area of sector, and we know that that is a half r squared theta. So we can take our values. We know that r is 10, so that's 10 squared for the r squared, times by the angle we've just calculated, 1.5. So that's a half times by 100 times by 1.5. Now, 100 times by 1.5 is 150, and we want half of it, so that is 75 centimetres squared. So that's the area of this sector. Further question we could ask is, what's the area of the segment, the minor segment? If you take a line across a circle, it divides the circle into two parts, a big bit, the major segment, and a smaller piece, the minor segment. And we can ask, what's the area of that minor segment? Let's just draw another diagram and look at that again, because there was quite a lot of vocabulary in that, quite a lot of words. So, we're going to take a line across the circle. We're keeping this as 15. And we've got the centre of the circle, and we know what the angle is. So there's R, we know that to be 10, and we've calculated what this angle is. So here's the line that we drew across the circle, and it divides the circle into two parts, a big part like that, which we call the major segment, and a small part like that, which we call the minor segment. And the question is, what's the area of this minor segment? How can we work it out? Well, we know the area of the sector of the circle. Area of sector, because we calculated that, and that was 75 centimetres squared. What we need to be able to do is work out the area of this triangle. Area of the triangle AOB. And the area of the triangle will be a half r squared sine theta. So that's a half times by 10 squared times by the sine of 1.5 radians. And again, we can work this out on a calculator. We have to be very careful that our calculator is set up to work in radians, not in degrees, to work in radians. And so here we have a half times by 100 times by, and the sine of this angle is 0.997, and then lots of decimal places. And if we work that out on a calculator, we get 49.8747. And so our final answer, which we want, is the shaded area here, the area of the minor segment, and that's got to be the difference between the area of the sector and the area of the triangle. So that's 75, take away 49.8747, and to a suitable degree of accuracy, 2 decimal places, that's 25.13 centimetres squared. Let's have a look at one final example. We have converted radians into degrees, but one of the things that we haven't done is to convert an angle that's in degrees into radians. So, let's take an angle 120 degrees. What is this angle in radians? Well, let's start off with our relationship that pi radians is 180 degrees. Now, we were able to say that 1 radian was 180 over pi, dividing both sides by pi. So if we want 1 degree, then we can divide both sides by 180. So pi over 180 radians is equal to 1 degree. We want 120 degrees. So pi over 180 times 120 is equal to 120 degrees. And again, we need a calculator to work this out, and when we work it out, we get 2.09 radians, and that's to 2 decimal places is the same as 120 degrees. The important things to take away from this video are this relationship, pi radians is 180 degrees, and the 2 formulae that we had, one for the arc length, which was S equals r theta, and one for the area of the sector, which was area of the sector is equal to a half r squared theta. And both of these to apply when theta is in radians.